Okay. Now concentrate. Yesterday we have discussed three experiments, right? Uh, which was those? We have discussed about the design of full adder, half adder. Okay. Then uh, design of 3S to 8 decoder, 4-bit parallel adder. So all of all of those we have discussed yesterday. Okay. Now today again we will proceed with the further design, that comparator part. Now we will discuss the design of comparator. How to design comparator, how to write VHDL code for the comparator, that we will discuss today. Now simply, what do you mean by comparator? If you take example of 2-bit comparator, what it means? So here is the truth table. 2-bit means A and B. These are the two inputs or the two what we can say bits that we supposed to compare, and each of 2 bits. That means A0 A1 and B0 B1. So these are the two different entities, and that we have to compare, right? And each entity is of 2 bit. Each entity is of 2 bit, means A0 A1 and B0 B1. Now we have to compare or the bit of the these two entities. That means whether this A is greater than B, whether this A is less than B, or whether this A is equal to B. That means we have to compare this A and B, two different entities, and we have to come out with the result. Means whether it is greater, whether it is equal to, or whether it is less than something or someone, right? So this is what the comparator means. And as it is a 2-bit comparator, so even you can go for 1-bit comparator. In 1-bit comparator you will have only 1 bit. A is of 1 bit and B is of also 1 bit. If you want to go for 4-bit comparator, that means A is of 4 bit, that means A0 A1 A2 A3, and B is of 4 bit, B0 B1 B2 B3. So you can go for n number of n bit comparator, doesn't matter. But for example, here we will design 2-bit comparator. Okay. So here is the truth table. I hope you are through with this. Now this is the block diagram, right? So actually this is how the comparator works. This is for n-bit comparator. N can be anything. N can be anything, but must be power of 2 only. N can be anything. This is the word A, word B. It can be of n-bit. It also can be of n-bit. And here is the result. Whether after comparison, after comparison, you can decide whether A is less than B, whether A is equal to B, or A is greater than B, so that you can decide. So this is the comparator. Now we will discuss the actual VHDL code for this. Now this is the VHDL code for comparator. This is the VHDL code for comparator. As usual, we have to start with the libraries. Now, can anyone tell why I have included libraries same IEEE, but why I have included these many different packages? Can anyone? These are the different packages. This is the standard logic 1164. This is the one package. Standard logic underscore arith. This is the second package. And standard logic underscore unsigned. This is the another package. Library same. IEEE is the single library. In that library, this is the package, and in that package, these are the items that we are going to use. Almost all items we are going to use. That's why, or in general, again, need not to mention any specific item. If we mention all, so we can access that entire package. So normally dot all, that means all item we supposed to access within that package. Now my question is, why we require these two package additionally? Along with this is a common package. Standard logic 1164, this is the common package. But again, why we require this arith package and unsigned package? Can anyone? Can anyone able to tell this? Why we require these two additional package, standard logic array and standard logic unsigned? Okay, what operation we are performing here? Operation of comparison. That means we have to decide whether something is less than, or whether something is greater than, or whether something is equal to. Now this less than or equal to, that means this signed unsigned characteristics or this arithmetic properties are included in this package, standard logic arith and standard logic unsigned, and that's why we supposed to use these packages for this program also, right? That means I have already told you, depending upon your application, depending upon your program, you have to decide which packages that you require, and you have to include that in your code, right? So this is all about the depends on the application, and that will be the how the coder is through with the concepts, and all about its wisdom. Okay, so this is the library part. Then after library, what should be there? Entity part. So this is the entity part. In entity, what we have defined? A, B, input, standard logic. Now in this case, we are considering A, B as a single bit. A, B as a single bit, because we haven't mentioned anything. Vector we haven't mentioned. But if you want to have the A of 2-bit and B of 2-bit, then what changes should I do here? It should be input standard logic vector 1 down to 0, right? Input standard here input standard logic vector 1 down to 0. This change I should made here, right? And GR is nothing but greater, LS is nothing but less, and EQ is nothing but equal, right? So these are the conventions that we are using to understand whether it is greater than or less than or equal to. So these are the three outputs. A and B are the inputs. Now we have defined the entity. Now actually we will start with the architecture part. Now again in architecture we are using the behavioral style, and if we are using the behavioral style, of course process statement has to be there. So we are using the process statement. Now the process A comma B begin if A is greater than B. That means if A is greater than B, then greater should get the value 1. That implies A is greater than B. That means if you find that greater has been allotted with the 1, that indicates A is greater than B. Else greater will get the value 0, right? Else this greater will get the value 0. Next, if next condition we are now we have to put now. If A is less than B. Now if A is less than B, then what you supposed to get? Less should get the value 1, else less should get the value 0. Less should get value 1, that indicates A is less than B. And of course the last case will be if A is equal to B, then this EQ, that means equal to, will get value 1, else equal to will get value 0. That means now suppose if condition is we have A and B is same, A and B is of equal magnitude, then now how this program will execute? Now first it will check whether A is greater than B. It will find equal. Then what it will do? It will allot greater with a 0 value, right? It will force greater with the value 0. Then and if this loop will get end, then the what we can say, the synthesizer will jump onto this loop, or synthesizer will again will get inside into this loop. Now it will again check whether A is less than B. No, this condition also holds false. Then what it will do? It will allot less with value 0. Then again compiler enters into this loop. Then it finds, yeah, A is now greater than B, and then it will allot equal to with value 1, and it will end the process, and of course end the architecture. In this way this code will get executed. Understood? This is about the comparator design. Understood or not?
Yes, sir.
Okay,
Yes,
fine.
sir.
Now we will discuss the next part, that is multiplexer. What do you mean by multiplexer? What do you mean by multiplexer? Many to 1. And demultiplexer means 1 to many. That means if you want to get a single output out of many output, you should use multiplexer. Now you can use n as to 1 multiplexer. You can have 2 as to 1 multiplexer. You can have 4 as to 1 multiplexer. You can have 16 as to 1 multiplexer. Right. And here, of course, there should be some enable pin as well as select pin. Here should be enable pin as well as select pin, right? And this D0, D1 up to Dn minus 1, these are the inputs, and this Y is the output. Clear with this? So this is the multiplexer. Now we will this is the truth table of multiplexer. This S0, S1 are the select lines. Means if S uh, both S1 and S0 is 0, 0, then at the output the D0 will appear. At the output side, D0 will appear. If any one of the bit out of S0 and S1 is 1, then at the output D1 or D2, depending upon which combination combination arrives. That means whether combination is 0, 1, then D1 will get at the output side, and if combination is 1, 0, then D2 input bit will appear at the output. And if both bits, that means both S1 and S0 is 1, 1, then the last one, D3 input pin will appear at the output side. So this is how multiplexer works, right? So this is the simple code for multiplexer. Again, we have to start with the library. This is the library part. We are using simple one package, standard logic 1164. This is the sufficient for multiplexer. Then entity mux4 is as why? See, this name you can decide by yourself also. It is not necessary that you have to mention this name only. Even you can give your name only, your name also, no problem. So what name you should give to the entity is up to you. It is there is no any hard and fast rule for that. Okay. Now this is the entity. I have given the name mux4. That means mux4 as to 1. So we have 4 input and 1 output. Now for 4 input, how many select lines we will require? 2. Right. For 4 input, how many select lines we require? 2 select lines. So select line input standard logic vector 1 down to 0. That means 2 bit we require. Input is of 4 bit, that means 3 down to 0, 4 bit, and of course output is a single bit. So select and A is the input and Y is the output, right? So this is the entity part. Now this is the architecture part. Now what we have written in architecture? Again, a behavioral, right? We are using the behavioral model. Begin. Y will get A0 when select is 0, 0. That means directly we are stating the conditions here. Directly we are putting the condition here and we are actually producing the output. That means if this is the condition, that this will transfer to the output. In that way we are actually coding. So Y will get A0 value when select is equal to 0, 0. Else means if this condition is not true, then it will check the next condition. Next condition is what? Then A1 will get Y if select is equal to 0, 0. Means what? In this case, the select line will define what input should appear at the output, right? Depending upon the select pin, that decides what input that will appear at the output. That means select is 0, 0. A0 will get appear at the output. If select is 0 1, A1 will appear at the output. If select is 1 0, A2 will appear at the output side. And last case is if select, that means S0 and S1 is 1 1, then A3 will appear at the output. So this is a very simple logic of to design a 4:1 multiplexer. Now the same logic you can extend for the 16:1, for the 32:1. So that is all, right? The same logic. Now if you want to design 16:1 multiplexer, how many select lines you will require? For 16:1 multiplexer, how many select lines you require?
4.
4 select lines, right? You require a 4 select lines. Means here will be the 16 inputs, and when select is equal to 0 0 0 0, that means a 16 combination you have to write with the select, and your job is done. You will get 16:1 multiplexer. Instead of 2 combination, here you have to write 4-bit combination and such a 16 cases. 4-bit combination and 16 cases. If you write, this same program will work as a 16:1 multiplexer. And of course, here also you have to change. Select line here should be 3 down to 0 and input 15 down to 0. If you made these 2 changes in this port, means entity, and with the select line, everything will be the same. 16 cases, such as 16 combinations will appear here, and each combination of 4-bit. That means with select pin, it is a 4-bit, and you have to write such a 16 combination, and for each combination, every a single input will appear at the output. That's all. These many changes, if you made with this program, it will execute as a 16:1 multiplexer. The similar logic you can extend for the 32:1 multiplexer. Similar logic. Just you have to change the input bit, input bit, select line bit, and here you have to write that many cases. That's it. Your job is over. Clear with this? This is the 4:1 multiplexer. Now we will discuss the flip-flops. Okay. Now have you studied flip-flops in your digital technique subject?
Yes, sir.
Okay, you have studied that. Fine. So what are different flip-flops available?
Yes, sir. JK, D flip-flop, T
SR
flip-flop.
flip-flop is there, right? JK, D flip-flop is there, and T flip-flop, that is toggle flip-flop. Very right, very right. So we have D flip-flop. Now again, I hope need not to explain the working of D flip-flop. I hope you are clear with the working, because already you have studied that, right? How D flip-flop works, how JK flip-flop works, how SR flip-flop works, and of course the last one is toggle flip-flop. So already you are aware of that. So I will just explain the coding part, how to actually write a code in a VHDL for these different flip-flops, for D, for SR, for JK, and of course T flip-flop. So this is the truth table of D flip-flop. All of you are clear with this? If clock is 0 and D is 0, then Q will get value of Q, and Q bar is Q bar. Then if clock is 1, D is 1, then Q will get Q. That means it will remain unchanged, and of course at Q bar it will be the simply component of the Q. Now if you enable the clock, that means if now clock is equal to 1, then what happens? And if D is equal to 0, then as the input is 0, it will simply transport at the output side. That means Q will be also 0, and Q is nothing but complement of this. That means 0's complement is 1. Similarly, if clock you have enabled and D is 1, then it will get transferred to the output. That means Q will also get 1, and Q bar is a complement of Q. That means 1's complement is 0. Clear with this? So this is the truth table for D flip-flop. Now JK flip flop, you are all of aware of. This is the block diagram of JK flip flop. J, K and clock, Q and Q bar is the output. Now this is the truth table for JK flip flop. This is the truth table for JK flip flop. If J is 0, K is 0, output will Q plus N will get value of Qn. If J is 0, K is 1, then output will get value of 0. If J is 1, K is 0, then output will get value of 1. And last case is if both, that means J and K is 1, 1, then it will get Qn. So this is the JK flip flop. Toggle flip flop, what it does, simply whatever the output, exactly the complement of that will appear at the output side provided with the clock. That means this is the truth table for toggle flip flop. If T is the input and Q plus N is the output. Now if input is 0, you will get Q1, and input is 1, you will get Qn bar. You will get Qn bar. That means exactly opposite to the input. So this is about the toggle flip flop. Now we will discuss the actual how to write this in a VHDL. How to design these flip flops in by using VHDL. So this is the VHDL code for D flip flop. We have to define first library, then entity part, right? In entity, what are the inputs? D and clock are the input and Q is the output. And this is the architecture part. That means this is actually the logic that we are using. Now, as we are using the behavioral, we can use clock process statement. So process clock. That means every process or every statement inside the process that depends upon the clock. Now, if clock is equal to 1 and clock tick event, that means this is the what we can say internal clock that is provided in VHDL. Clock tick event means what? If clock has triggered, its meaning is clock has triggered. Now, if clock is equal to 1 and clock tick event will occur, then Q will get value of 0. Then Q will get value of D, means whatever the input, that will be a 1, that will be a 2, provided that clock has to 1. If clock is not 0, it will simply jump out of the loop. It will end process and end behavior, and in that case the output will be the previous state only. That means whatever the output previously was there, that will reflect as it is. That will reflect as it is. And if clock is 1, then only output will change. If clock is 0, output will not change. It will remain as it is. Okay. So this is about the D flip flop. Now toggle flip flop, T flip flop. This is the library part. This is the entity part, and this is the architecture part. Now in architecture, what we have did, architecture behavioral of T. Now here we have defined one signal. This temp is the signal name, and it's of type standard dot logic. That means it's what we can say, the mode. Mode now. Class of the signal. This is the class. What class? Data type class is standard logic. This is the class. Temp is the signal name, and of course this is the syntax for signal. So temp is the signal. This is the signal name. Okay. Then begin process clock. That means everything that is depend upon the clock process. Now here again we have used the same logic. If clock tick event and clock is equal to 1, then if T is equal to 0, then temp will get value of temp. That means this signal we are using to pass the value even within the process, and simply we can pass outside the process also. Means if T is equal to 0, then temp will get value of temp, and else if T is equal to 1, then temp will get value not of temp. Not of temp. That means if T is equal to 0 and provided that clock is equal to 1, then temp will get value temp only. Else if T is equal to 1, then it will get value not of temp. That means exactly complement of this temp. Complement of this temp value. So this is the toggle flip-flop. And if, and process, and finally after process we have to again allot this signal value back to original output. That means Q was the original output. The signal we are using the to pass this value we what inside the process to the that output. That's why you have used the signal here. We cannot use variable because you can see here we are passing this value after ending the process. After ending the process, if we might have used the variable here, we cannot use variable outside the process. If we want to use or if you want to pass that this temp value outside the process, it has to be signal only, because signal has the capability to pass any value outside the process, and that's why we have used signal here. Now this signal value we have allotted back to the original output, and we have ended with the behavioral model or behavioral architecture. So this is a very simple program to design a T flip-flop. Similarly, we can design JK flip-flop also. This is the library part, right? This is the library part. This is the entity part. JK and clock is the input. Q and QB is the output. Now, here we have begin with the architecture. Again, we have used the process statement. Clock, that means everything depend upon the clock process. Variable temp. Now here we have used the variable, and that to be a inside process. But now you can see here we have used the signal, and that we can use outside the process. प्रोसेसच्या पहिले आपण ते यूज केले का, कारण एका प्रोसेस मधली व्हॅल्यू जर का तुम्हाला प्रोसेस नंतर पास करायची असेल तर ते सिग्नलच करू शकतं, व्हेरिएबल करू शकत नाही. का, आपण शिकलो व्हेरिएबल हे प्रोसेस पुरतं मर्यादित असतं, प्रोसेसच्या बाहेर त्याचं मिनिंग नाही. मग तुम्हाला एखादी इनसाइड द प्रोसेस व्हॅल्यू आउटसाइड द प्रोसेस पास करायची असेल तर त्यासाठी तुम्हाला तो सिग्नल आधी डिफाइन करून घ्यावा लागतो. विथ द हेल्प ऑफ सिग्नल यू कॅन डू दॅट, बट विथ द हेल्प ऑफ व्हेरिएबल यू कॅनॉट डू दॅट. मग इथे आपण व्हेरिएबल डिक्लेअर केलाय म्हणजे तो फक्त विदिन प्रोसेस व्हॅल्यू पास करू शकतो, आउटसाइड द प्रोसेस व्हॅल्यू पास करू शकत नाही. दॅट्स वाय वी हॅव युज्ड व्हेरिएबल हिअर अँड अवर रिक्वायरमेंट इज दॅट ओनली. आपली रिक्वायरमेंट पण तेवढीच आहे, आपल्याला ती व्हॅल्यू आउटसाइड द प्रोसेस पास करायचीच नाहीये, पण या केसमध्ये करायची होती आणि म्हणून आपण इथं सिग्नल डिफाइन केला होता. प्रोसेस देन व्हेरिएबल टेम्प. टेम्प हे व्हेरिएबल आपण डिफाइन करून घेतलं, दॅट इज ऑफ क्लास स्टँडर्ड लॉजिक. बिगिन इफ clock is equal to 1 and clock tick event happen, then if j is equal to 0 and k is equal to 0, then temp will get value temp. म्हणजे जे काही व्हेरिएबल तुम्ही टेम्प स्टँडर्ड लॉजिक यूज केलेला आहे that will get remain same, that will get remain same. Next condition, else if j is 1 k is 1, then temp will get value not of temp, temp will get value not of temp. Third condition, else if j is equal to 0 and k is equal to 1, then temp will get value 0, temp will get value 0, else temp is equal to 1. This else means for the remaining condition. What is remaining condition? J is equal to 1 and k is equal to 0. For this remaining condition, temp will get value 1. And if now here you can see here, before ending the process we have passed that temp variable to the output. Before ending the process end करायच्या आधी आपण ते व्हेरिएबल ओरिजिनल आउटपुटला आपण त्याची व्हॅल्यू पास केली. हे सेम लाईन जर का तुम्ही इथे लिहिली असती आफ्टर प्रोसेस, यू माइट हॅव गेट एरर, यू माइट हॅव गॉट एरर, तुम्हाला एरर आली असती. का, यू कॅनॉट पास व्हेरिएबल आउटसाइड द प्रोसेस, यू cannot pass variable outside the process. बरोबर आहे, हेच आपण युनिट नंबर फर्स्ट मध्ये सगळं शिकलेलो आहोत. and obviously q will be the exactly not of temp, complement of the temp. So this is how you can design this different flip-flops used in VHDL programming with the help of this Xilinx tool, right? After at the completion of this theory part, definitely I will demonstrate you with one or two examples how to actually perform the code and how to execute this VHDL code using that Xilinx simulator that I am going to demonstrate you after completing this theoretical part. Okay, first I will explain you all the codes and its logic, and then at the last I will demonstrate you how to execute that with the help of Xilinx ISC suite. Okay. Okay, so this is about the flip-flops. Now, next is a 4-bit shift registers. 4-bit shift registers. This part we will discuss in tomorrow's lecture. Okay, today we will stop here. Have you clear with these three programs? Comparator, multiplexer, and flip-flops. Have you clear with this? If you have any doubt, you can ask me right now. If you have any query, you can ask me right now. कुणाला काही शंका?
सर जेव्हा आपण व्हॅल्यू असाइन करतो ना 0 किंवा 1 तेव्हा लेस दॅन इक्वल टू घेतो. डायरेक्टली इक्वल टू का नाही घेत सर?
कुठल्या प्रोग्राम मध्ये म्हणताय तुम्ही?
सगळ्याच प्रोग्राम मध्ये सर. आर्किटेक्चर मध्ये जेव्हा आपण असाइन करतोय ना व्हॅल्यू तेव्हा सगळीकडे लेस दॅन इक्वल टू घेतलं. डायरेक्टली इक्वल टू का नाही घेत?
नाही, कुठे लेस दॅन इक्वल टू घेतलं? व्हॅल्यू असाइनिंगचा सिम्बॉल काय? कोलन and equal to sign. Less than equal to. Acha, okay, you are talking about this. Oh no, this is not less than. You consider it as a arrow. म्हणजे हा arrow indicate करतोय की d ची व्हॅल्यू q ला ट्रान्सफर होते. It is not a less than sign. Actually, this is the symbol. Arrow followed by equal to sign. That indicates this d is passes its value to the q. Direction दाखवते ते. It is not less than equal to sign.
Okay, sir.
आलं लक्षात? This showing the arrow. That means how data is transferring from which variable to which variable. हे ते दाखवते. म्हणजे ह्याच्यात d पासून q ला व्हॅल्यू पास होते. हा arrow काय दाखवतोय? d ची व्हॅल्यू q पाशी जाते. This is the arrow. Actually, you can take it as a direction sign. This is not a less than equal to. Actually, you have to represent that a less than equal to. तुम्हाला ऍक्च्युअली प्रोग्राम मध्ये लेस दॅन इक्वल टूच लिहावं लागतं, पण इट इज नॉट लेस दॅन अँड इक्वल टू. द टुगेदर इफ यू लुक ॲट दॅट इट विल लुक ॲज अ ॲरो. ते जर का एकत्र तुम्ही बघितलं तर तो ॲरो सारखा दिसतोय का नाही? सो दॅट इज ऍक्च्युअली द ॲरो दॅट टेल्स द डायरेक्शन ऑफ डेटा पास. म्हणजे डेटा कुठनं कुणापाशी जातोय ह्याची ते डायरेक्शन दाखवतं. यू कॅन टेक इट ॲज अ ॲरो. Okay, though you are representing with the less than and equal to sign, but if you combinedly consider that, it will look like a arrow. So that's the telling the direction of data flow. Okay, समझला?
हाँ sir.
Okay, fine. So we will stop here. In next lecture, we will again study some of the designs, right? And how to write a VHDL code of that design. So we will discuss the 4-bit shift register, then ALU, right? And one more design. Okay, so that we will discuss in next lecture. Today we will stop here. I hope you are through with this.
Sir,
बोला.
PPT शेअर करता का ग्रुपवर?
Okay, this is actually the lab manual also and PPT also. Yes, I will share on your group. No problem. Okay, I will share with you this slide. No problem. Okay, we will stop here.